This is not about like replacing JavaScript. It's about how can we bring JavaScript to places where you don't really have access to JavaScript normally. So one example is like serverless environments that just run WebAssembly. How do you run JavaScript in this environment? Or there's, different environments or OSs that you don't have a JIT compiler. And so all you have are the options of like running an interpreter. And so we have kind of like a wacky setup that, surprisingly works pretty well where, yes, we're taking SpiderMonkey, which is Firefox's JavaScript engine, and we're compiling that to WebAssembly. So we have, a JavaScript engine running inside of WebAssembly.
Big thanks to our partners Linode, Fastly, and LaunchDarkly. We love Linode. They keep it fast and simple. Check them out at linode.com/changelog. Our bandwidth is provided by Fastly. Learn more at fastly.com and get your feature flags powered by LaunchDarkly. Get a demo at launchdarkly.com. This episode is brought to you by Retool. Retool is the low-code platform for developers to build internal tools super fast and super easy. They have a ton of integrations and templates to start with. With a click of a button in seconds, you can start with a new Postgres admin panel application, kick off an admin panel for reading from and writing to your database built on Postgres. This app lets you look through, edit, and add users, orders, and products. It's too easy to get started with Retool. Head to retool.com/changelog to learn more and try it for free. Again, that's retool.com/changelog.
This is JS Party, your weekly celebration of JavaScript and the web. A quick note about this episode. The day of recording, Nick was dog sitting for a friend who was in the hospital. The dog was agitated due to the new environment, and there weren't many options or workarounds for us. So you will hear some barking scattered throughout, especially in the first 5 minutes. The conversation is a good one, and it's definitely worth your while, despite the distractions. Thanks for understanding, and I hope you enjoy it. Okay, let's do this. Hey, it's party time, y'all.
Hello, JS Party people, and welcome to another wonderful episode of your favorite party about the web on the web. We are live streaming right now. I have our one and only Nick Nisi joining me today.
Hoi hoi.
Hey, hey. Mr. Burns. We may be calling him Mr. Burns through this episode because our special guest today is Mr. Nick Fitzgerald, who is a staff engineer at Fastly. Hey, Nick.
Hey, how's it going?
Hello, hello. And I, of course, am your MC this week. I'm KBall coming at you. We are super excited to talk with you, Nick. Thank you for joining us today. The impetus for this was I saw a really cool article talking about making JavaScript run directly on WebAssembly. But before we get into that, can you tell us a little bit about yourself, your background, and what kind of stuff you do?
Yeah. So I used to be at Mozilla, where I started on the developer tools team. And I did that for a bunch of time. And then kind of one Christmas break, I was thinking, so let me back up a bit. I was the author and maintainer of the source map library. And it was something that we always had trouble with for like larger programs, right? We'd get really big source maps, 15 megabytes, 50 megabytes, whatever. And starting up the dev tools would take a long time because we just sit there parsing these large source maps. And the parser was all written in JavaScript, and we were writing this like really, contorted JavaScript. Like we were avoiding exceptions, we were avoiding allocating objects. So we would like use the same single object as an out parameter every time we called functions and like write to those properties because, allocation was too slow, and then we get GC pauses. And so one Christmas break, I kind of got annoyed and fed up with this, and I decided to rewrite it in Rust and target that to WebAssembly, and ended up making it a bunch faster. I forget what the exact numbers were. This is quite a while now. But that was kind of like my intro to WebAssembly and how I got kind of involved there. And then as it turned out, Mozilla was spinning up a team to work on WebAssembly stuff, different from the people who are working on WebAssembly, like the engine directly that's inside SpiderMonkey. And so I joined that and then stayed with Mozilla for, a while, and then ended up moving to Fastly with a bunch of the rest of my team. And so that's kind of how I got here.
I remember when that first came out with the source maps. I somehow hadn't made the connection that was you, but it's like it was 10 or 11 times faster than the original implementation.
Yeah. And then mralif or Mr. Alif, I'm not sure exactly, what he goes by. He kind of took it as a challenge and took the original JavaScript and made that a bunch faster and kind of got it close in the neighborhood of where the WebAssembly was. But what was cool is that all of his techniques for speeding up the JavaScript were algorithmic. And so I just took all those algorithmic speedups and applied them to the Rust and WebAssembly. And that got like another 5 times faster from what it was or something like that. So I don't know. That was really fun. A good little back and forth blog post series.
That's awesome. And then the latest thing that I saw and what kind of led to this was now you're working on a project that involves not just replacing JavaScript with WebAssembly, but actually running JavaScript using WebAssembly. I think compiling the entire JavaScript engine down to WebAssembly or something like that. Can you talk a little bit about this project?
Yeah. So, I don't really like the term replacing JavaScript, right? So I guess something I left out in my intro is I also was the lead of the Rust project's WebAssembly working group. And so it was kind of trying to make Rust and WebAssembly play nice with JavaScript. So our whole thing was that you shouldn't replace your JavaScript. Like they should, live together and be friendly. And so you can reach for just those kernels of really hot code and replace them with some Rust and WebAssembly, but then that should fit into your larger program. And so again, this is not about replacing JavaScript. It's about how can we bring JavaScript to places where you don't really have access to JavaScript normally. So one example is serverless environments that just run WebAssembly. How do you run JavaScript in this environment? Or there's, different environments or OSs that you don't have a JIT compiler. And so all you have are the options of running an interpreter. And so we have kind of a wacky setup that, surprisingly works pretty well where, yes, we're taking SpiderMonkey, which is Firefox's JavaScript engine, and we're compiling that to WebAssembly. So we have, a JavaScript engine running inside of WebAssembly, and then we run the JavaScript on top of that. And you might be thinking wow, that's got to be way slower than, running JavaScript how you would normally run it. And yeah, that's true for throughput, but not for latency. So latency is how fast can we start up the engine and respond to something? And throughput is how much work can we do extended? Or how long does it take to finish all of the work at a time? And so we have this tool that I developed called Wiser, which takes snapshots of WebAssembly and allows you to just basically, initialize a program, take a snapshot at that point in time, and then the result of that snapshot is actually itself a WebAssembly module. And when you instantiate that WebAssembly module, everything's already initialized, and so you don't need to do any of that startup again. And so what we can do is we can actually run all the JavaScript initialization. We can start up the JavaScript engine. We can parse the JavaScript, turn it into an AST, turn it into bytecode, evaluate the top level so that all the event listeners are registered and everything like that. And if the JavaScript needs to build a global lookup table that it does kind of in the top level, all that stuff happens. And then we take a snapshot. And then, so that stuff's already done. When we start up again, there's basically nothing that needs to happen. We're just immediately ready to start running JavaScript. And if you kind of compare this to starting up a V8 isolate, I think it takes around 5 milliseconds to actually start the isolate. And that's, you haven't even started processing the actual JavaScript source code at that point yet, right? So you would still need to then parse the JavaScript, emit bytecode, etc. And so with our snapshot, all that stuff is already done. And I think the kind of metaphor that Lynn made in her blog post was, if you have a contractor, you have to first negotiate with the contractor, hire them. That's kind of getting the JavaScript engine set up and, getting office space and stuff. And then there's kind of making the Trello board or whatever, right? And getting all those items ready. And that's kind of parsing the JavaScript. And then there's the actual work that needs to be done. And so we're kind of making an office in a box here where, you just open the suitcase and the office is all ready and everything is ready to go. And you don't have to do any of that kind of initial setup time.
That's super interesting. So can we actually step back for a second? Because I think You're way deep in the weeds on this in a way that I think not everybody has the context. So you mentioned a couple of things there that I'd love to dig into. So first, can you just sort of explain what is a V8 isolate? Because that was the comparison you're drawing.
Yeah. So a V8 isolate is basically like a little world of JavaScript in V8. So I'm actually much less familiar with V8 than I am with SpiderMonkey because I worked at Mozilla and I, hacked on SpiderMonkey a bit. But basically, the idea is that like any of the JavaScript within an isolate is kind of isolated from any JavaScript that you have in any other isolate. So like if you were developing a serverless platform and using V8 for that, you wouldn't want two customers' code to run in the same isolate because you really don't want them to be able to poke at each other's stuff, right? Like that's a huge security vulnerability. And so an isolate is kind of like the unit of like, it's kind of like a process in an OS. Or like, a different window in a browser or a different tab.
Got it. So it's like a self-contained JavaScript execution environment.
Exactly. Yeah.
Cool. And so then you were talking a little bit about the different phases involved with running code in an isolate, right? There's like instantiation, parsing, all these different things. So can you maybe break down a little bit like what was the motivation for this? Because I think we jumped right into also what does it do, but like maybe we can talk a little bit about the whys behind it.
Yeah. So the idea is just basically how can we bring JavaScript to environments where it otherwise wouldn't be? And, so for us, the big motivating thing, us at Fastly, is our Compute at Edge platform, where we just support WebAssembly and we would also like to have some JavaScript there. But there's, there's environments where you don't have access to JITs. And so maybe you would prefer to have this approach to get like really fast startups.
That was something that was new to me. This is not really my realm by any means, but the idea of a serverless environment for Wasm, like what are the practical uses of that?
Yeah, so we just talked about isolates, right? Mm-hmm. And a Wasm instance is kind of similarly sandboxed, right? Like there's a few different kinds of state that a Wasm instance has, but kind of the one that everyone knows about is the linear memory, right? You just have basically this big array of bytes, and that's kind of your sandbox to play in as a Wasm instance. And so it gives you kind of similar guarantees, but it's a lot simpler because that's it, right? There's just this array. We're not talking about like objects in a GC heap or anything like that. And so because it's so much simpler, we can, start it up a lot faster. Creating a new one takes, depending on the module, a handful of microseconds rather than, milliseconds. So like a whole order of magnitude faster. And WebAssembly has this nice property where it can only do stuff that it imports. So by default, WebAssembly can't really do anything. At most, it can kind of spin the CPU and cause some heat, and maybe you have to like interrupt it and say, stop doing that. But like if it wants to, talk to the network or write to disk or anything like that, you need to kind of give it functions that allow it to do that. And so it's kind of like a capability-based security, if you're familiar with that, which is basically like you don't have the capability to write to the network or communicate on the network unless I give that to you.
Okay.
And so you get these really nice, security and sandbox properties. And so that's kind of why we're interested in that in serverless, because we can do it, create more instances faster than kind of, alternative approaches, and we can pack more of them together in one machine.
That's cool. That's a good reason for that I hadn't considered. So if, like, without getting on too big of a tangent, if JavaScript isn't typically available there, like what is the primary language that is typically targeted with a Wasm serverless environment?
Yeah. So Rust is a big one.
Okay.
And also some people use C and C++. There's AssemblyScript, which is probably more familiar feeling to people who are familiar with JavaScript. Kind of the idea is that it's kind of JavaScript syntax that maps pretty much directly to WebAssembly.
Gotcha.
And so it'll look familiar, but might feel a little bit different, kind of based on the restrictions of targeting WebAssembly.
What's up, party people? This episode is brought to you by Micro. Micro, aka M3O, is a new cloud platform built for developers by developers. Our good friend Wasm is leading this. And if you're tired of AWS and feeling overwhelmed by the cloud, infinite billing, and an endless sea of docs, it is time for a change. The Micro team is reimagining the cloud for the next generation. M3O is a new developer-friendly platform to explore, search, and use simpler APIs for everyday consumption, all in one place. Get access to the APIs you need in one click and test them right there on the web before using them. Simple, fast, and affordable. You won't get burned by bottomless billing. You top up your account and pay as you go. And right now, they're in early development and building out the first set of APIs, and they're looking for feedback from developers. Sign up and get $5 in free credits. Kick the tires, give them your input so they can build the best APIs you want to use every single day. Learn more at m3o.com. Again, m3o.com.
Awesome. So, Nick, you were sharing some about the motivations and some of the pieces there around running in places where you wouldn't otherwise be able to run this. But you've also alluded a lot to performance benefits and trade-offs. And I'd love to dig in a little bit more then on what you accomplished, because you started this based on, okay, we want to be able to run this in our Wasm environments. But the blog post that Lynn put together, you also highlighted some really intriguing performance improvements, and you sort of alluded to that in your startup times. But yeah, can you walk us through, like, what did you find out? How does this thing run relative to those isolates or relative to a native JavaScript environment?
Yeah. So starting up the JavaScript engine, and creating an isolate or kind of SpiderMonkey's equivalent, takes around 5 milliseconds. And then actually, then once the JavaScript engine is created, you have to give it the source code for your application. And so then that involves parsing and all this stuff. And so it can take quite a while, maybe up to like 50 milliseconds or something before your application is ready to respond. And people have shown all over the place that the faster you can have your pages load, the more customers will, click checkout, and, generally the happier they are or whatever. Right. And so kind of having, the speed of light, the fastest that you could potentially go, be on the order of 50 milliseconds, or, even if we got it down to 6 milliseconds, right? That's it's not great. People fight hard to get better times than that because it's worth it. So that was kind of a no-go for us. And so what we wanted to figure out was, how could we have basically instantaneous startup? And that's kind of where my whole snapshotting work comes in. And
does it achieve that then? It's essentially
so
unmeasurably fast?
We're talking microseconds. So, I think for the JavaScript engines, it's around 300 microseconds. For a Rust program, you're looking at maybe 30, 40 microseconds. That's, pretty dang near instantaneous.
That's wicked fast.
Yeah.
Okay. And you mentioned that there are some trade-offs in terms of throughput if you end up then executing a fair amount. Have you kind of measured those curves over time? Like, how long running of a function does this need to be before it starts to kind of swap over to being less efficient?
Yeah. So there's some subtlety there, which is if you look at, say my program takes 1 second end to end, right? It's well, how much of that 1 second is actually bottlenecked in JavaScript execution? Right? Are you doing I/O, reading from disk, or, communicating with the network or whatever? And not every program, but many programs are basically just kind of gluing together I/O. And so in these cases, even if you had the most advanced, JIT, V8 or SpiderMonkey or JSC, you still wouldn't ever actually get to those top tier JIT levels, right? Maybe you would break out of the interpreter into kind of a baseline compiler, but you probably wouldn't break out of the baseline compiler into the top level compiler. And so JavaScript throughput for many programs, not all programs, it doesn't really matter. And so that's kind of the area that we're trying to do well in right now, because the truth is, if you have something that is bottlenecked on JavaScript execution, this is going to not work super well, right? Because We are using just an interpreter. There's no JIT compilation happening here. And it's running in WebAssembly rather than native. So there is like a little bit of overhead. It's kind of stuck on there. But if you're gluing together IO, then you'll have a great time. And the other option here is there's a proposal for WebAssembly called module linking that we're kind of driving forward and we're in the process of implementing. And so what module linking does is it allows you to kind of create, similar to like a Webpack bundle, where you are bringing together a bunch of different JavaScript modules. It's kind of similar, but for WebAssembly. And so it's the same kind of vision that we were pushing on the web for Rust and WebAssembly working group, where we were saying, take your core compute that's actually bottlenecked on the CPU and write that in Rust, because it's just easier to write that kind of code in Rust than it is in JavaScript. And then just make it fit into the rest of your JavaScript. And so with module linking, what we can do is you can say, hey, take that core compute that's actually bottlenecked on CPU, compile it to WebAssembly with Rust, and then link that in to your JavaScript program that's running, on the stuff that we've been talking about. And you can actually import that as a JavaScript module. And then, any of the stuff that actually needs to be fast, you can kind of just push onto the other side of that boundary.
That makes a lot of sense. Interesting. So this type of moving dynamic runtime environments and sort of just-in-time or interpreted languages into running within a compiled context, linking in compiled modules when fast. I feel like we've done that a lot on server side, but doing WebAssembly lets us do it anywhere we might want. Do you see a similar approach being applied to other languages besides JavaScript?
Yeah. So what's cool about this approach of getting fast startup with snapshots is that it's not specific to JavaScript at all, right? Like if you happen to love Ruby more than JavaScript, like you could do the same thing with Ruby and its interpreter, or Python or Lua. It's just as long as it can target WebAssembly, it's kind of just, it's a feature of how simple WebAssembly is that we can take these snapshots and make them start up really fast. So basically anything that can go to WebAssembly, we can do this same technique on.
That's super cool. Does Fastly support that today?
So it's an open source tool. So this isn't something that we're like kind of hoarding the magic and, doling it out as we please. Like you can download the tool. It's on GitHub, Bytecode Alliance /Wizer, WIZER, because it's the Wasm initializer, Wizer. And then someone suggested that we call these modules after, the snapshots as wizened modules, because now they already know everything that they need to start up. Yeah.
How did you spell that?
WIZER.
Okay. We will include a link in our show notes for all who are interested in that.
Yeah. And if people are really interested in the snapshot side of things, I gave a talk at this year's WebAssembly Summit specifically about Wizer and how it works. So I can share a link with that after the show.
Yeah, that would be super cool. So where do you see this going? I think we're right now at the cusp with tools like this. And, we had an episode a few weeks back where we were talking with the team behind Stack Containers or something where, they're basically running StackBlitz, yes, and web containers, where they're talking about running Node.js and other server-side environments in the browser and things like that. So we're kind of reaching this place where WebAssembly is letting us open all these new possibilities. What do you see as the next frontier here?
Yeah. So specifically for this JavaScript on Wasm work, we're looking to take kind of the classic optimizations that JavaScript engines have used for improving throughput and applying them in kind of an ahead of time context rather than a just in time context. So what JavaScript engines do is they'll look at, this function is only ever called with 2 integers as arguments. And so I can optimize based on that. And, this, plus operation, it always gets these 2 integers. So I can turn that into, an addition rather than, string concatenation or having to check whether I'm doing addition or string concatenation every time. And kind of the way that happens are something called inline caches, which kind of are like, is it this type, then do this. Is it that type, then do this. And each of those do this is a little stub, an inline cache stub. And so traditionally, the way that inline caches have been done in kind of a JIT environment is, say we're reading a field of an object. It'll say, is every object has a shape or a hidden class, which is basically saying what are the order of properties that I have and kind of what is my prototype chain and that kind of thing. Normally, if you don't have any idea what the shape is, you have to kind of like look up in a hash table to see, okay, where does this field exist? And then let me get that value. And that's kind of an expensive operation for something that happens so often. But if you have an inline cache, you can say, is this object this shape that I've seen before, right? Like this function happens to always be called with objects that have the same shape. And then you can just say, if it is, then I know already, I've kind of baked in that the field that I want to read is at offset 8 or something like that, right? And that's just way faster. It's like a check and then an offset read. And so normally the inline cache would kind of bake in the pointer to that shape, and it would also bake in that offset. And those would kind of be generated in the machine code just in time. But what we can do is actually we can make the pointer and the offset parameters and make this inline cache like a little function that takes these things. And so now this doesn't actually depend on anything at runtime, right? Because, where the shape is in memory, that's something that's at runtime. But we've kind of pulled all the stuff that happens at runtime out, and we have something that we can use ahead of time. And so if you're baking in pointers and stuff, there's kind of an infinite number of inline caches that you could generate, right? But there's only like so many like types of inline caches, right? Where if you pull all these dynamic things that rely on what's happening at runtime out and you make them parameters, then you're left with just n different kinds of inline caches. And we can actually compile all of those ahead of time and then kind of like wire them up during execution, but without any kind of just-in-time compilation. This should get us our throughput around where JavaScript was at kind of the start of the browser wars, when Chrome was like first coming out and it was like so much faster than Firefox or whatever, right? And so that's the good first step. And then kind of the way that JavaScript engines get even faster from there is they start doing more aggressive optimizations than just like optimizing just the add, right? They kind of say, okay, assume that, this whole function, we only see integers. Don't optimize each individual operation, kind of optimize the whole function based on this and do lots of inlining and stuff like that. And we can't do any of that at runtime because all of this depends on watching what's going on at runtime and then compiling at runtime. But if you have kind of profile data, like if you run the program over some benchmarks and then you kind of record what happened, what types flowed where and which functions were called a bunch of times or not, you can basically gather that same data and then compile the JavaScript ahead of time. And so that's kind of like the next step on the horizon after that is basically do what JITs do, but ahead of time via some profiling, maybe. And that should get us, in principle, it's kind of tricky because you have to have a good benchmark set, right? Which is kind of the big hurdle here. But in principle, this should get our throughput basically to where JavaScript engines are in the browser today.
This is really interesting. So we're essentially talking about moving JavaScript to being more and more of a compiled language in a lot of ways, rather than an interpreted language with a JIT compiler. And as you talked about profiling, it made me wonder, you're already doing pre-compilation. You're already putting these things in an environment where they're going to run against the most realistic data there is, actual production data. How expensive would it be to put profiling information or profiling gathering there and over time recompile these same workers that you're deploying based on profiling data of their live application? Yeah,
that's kind of like the long term, right? We have a lot of stuff to build out before we can start thinking about that stuff. But yeah, you can do stuff like you don't need to profile every single, execution. You can sample. So it's exciting, but we have a lot of work to do before we can start doing that kind of thing.
Yeah, no, that is super cool.
Yeah, so we were also talking about like where are things going. That's one dimension for where JavaScript on Wasm is going. And then there's kind of this other dimension of where Wasm is going. And, Wasm is similar to JavaScript. It has many people who are invested who are kind of doing different things, right? So there's not like one direction that it's going. There's a bunch of directions that different people are taking it. But one of the directions that I'm really excited about and kind of alluded to is that module linking stuff. And so kind of, it's one thing to be able to like stuff WebAssembly modules together, but we talked about how simple WebAssembly modules are. And that means that there's not really a good way to communicate advanced structures. Because so WebAssembly has, MVP WebAssembly, kind of base WebAssembly has, 32-bit floats, 64-bit floats, 32-bit integers, 64-bit integers. And so that's not a lot of ways to communicate
and that's
with each
it.
other. That's it, right? And so what compilers do is within the memory, they'll lay out where structures are and stuff. And, the same way they would lay it out in native memory. But if I'm a Rust program and I want to talk to a C program, C doesn't really understand Rust data structures. Rust can kind of talk at the C level, but it's a little bit painful. And now we're talking about interacting with JavaScript, but not even just JavaScript directly, but JavaScript running inside SpiderMonkey, a JavaScript engine that's on Wasm. And so the structures are just totally foreign, and communicating is really difficult. But this is where another WebAssembly proposal comes in called interface types. And so interface types are basically a type grammar, sort of similar to WebIDL, where WebIDL defines, here's records, here's, different string types, et cetera, et cetera. Interface types defines a similar type grammar. And then the idea is you'll be able to communicate like this. And interface types isn't quite an IDL in that the plan is eventually you'll be able to kind of have dynamic adapter functions that allow you. So say you're receiving a string over this interface types boundary that lets modules communicate. And Rust's strings are represented as UTF-8. And so it'll want to just lower that into a flat UTF-8 array. But JavaScript strings are much more complicated. So in SpiderMonkey, I think there are, I forget if it's 7, 9, or 13, but it was one of those kind of odd numbers like that, different representations of a string. And so maybe the coolest one is called a rope. And so what a rope is basically a tree of little strings. And so the idea is if you concatenate two strings and your string representation is just a buffer, you kind of have to, potentially grow a new buffer that's the size of both of them. And then you have to copy the strings in. And it's really expensive. That's an order n operation. But if you have a rope, what you can do is you can just say, it's kind of a tree. And so you have a node that's just, I'm the concatenation of this one string and this other string. And creating that is, order 1. And so it's very cool, but it's very complicated. But interface types kind of will eventually allow you to define your own ways to kind of lower, kind of the platonic ideal of a string down into a rope or something like that, right? Kind of arbitrary computation for translating these types on either side. So that's kind of the furthest vision. But right now we're defining just kind of what's called a canonical ABI, which fixes the representation. You have to use, a string buffer or something like that. There's one representation for each type. And so with just the canonical ABI, it is kind of just like an IDL. But it's open to that next step once we, ship the first phase. And so this is going to allow all of these modules to talk to each other. And each of these modules, what's really key about interface types is that they're kind of shared nothing. So if you think about NPM modules, when you use an NPM module, it gets all the same permissions and capabilities that your application has, right? And this is a problem. We've seen this, supply chain attacks, right? Where, some generic, I'm a Markdown, library or something. I don't think it's actually happened with the Markdown library, but, I just do something very innocent. And then actually I'm, reading your SSH keys from disk and I'm sending them off to some server, or I'm, mining Bitcoins or whatever, right? And so it's not great. And so we talked a bit earlier in the podcast about capabilities and how a WebAssembly module can't do anything unless you explicitly give it something to do. And so interface types kind of preserves that ability between different WebAssembly modules. So it says, just because I can read to the disk and I'm talking with you and I'm using your Markdown library, doesn't mean you can talk to the disk. All you can do is, take this Markdown
Ask
source.
me to talk to the disk.
Yeah, exactly. And so it kind of it limits the blast radius of where things can go wrong when you have a supply chain attack like that. They can't escape their sandbox, even if they're talking to you, because the only way you can communicate is with this type grammar, and you don't automatically get any access to resources unless I explicitly give them to you. So yeah, so this is the other horizon just kind of for WebAssembly in general. And we want, the JavaScript to be able to participate in this ecosystem, having this ecosystem of modules that share nothing, that don't implicitly give security capabilities and are all kind of sandboxed from each other even while they're working together. That's kind of the direction we're going.
What up, party people? If you want to know what's happening with your code, track errors, and monitor your app's performance with Sentry, build better software faster with Sentry's application monitoring platform, diagnose, fix, and optimize the performance of your code, cut your time on error resolution from hours to minutes. It works with any language and integrates with dozens of services. Over 1 million developers and 68,000 organizations already use Sentry. And best of all, JS Party listeners new to Sentry get the team plan for free for 3 months. Head to Sentry.io to get started and use the code PARTYTIME when you sign up. Again, Sentry.io and use the code PARTYTIME because, hey, it's party time, y'all.
All right, let me jump in with a quick and potentially dumb question, or a series of questions, I suppose. But it's really cool, and I know that this is an oversimplification, but it's kind of interesting to see, like, you know, out of JavaScript was born this WebAssembly. Not really, but, you know, in a way. And now we're figuring out how to get JavaScript back into WebAssembly. And I just, like, naively think that's hilarious. But is there a interoperability path between the two? Like, if I'm writing JavaScript for Wasm, do I have to think about writing that differently than writing JavaScript for like a browser environment or Node?
Yeah, definitely. That's a really great question. So it's SpiderMonkey, and it's not Node. It's not a web browser. It's just SpiderMonkey. So it's a much more pared down JavaScript environment than you would have on the web or on Node.
So I can't have like Node modules, obviously, or anything like that. And I don't have like any of the, you know, browser environments like Fetch or things like that are more supplied by the environment. It would just be the core language
so
itself.
There's no DOM nodes, for example, and there's no like require FS that you would have on Node.
Yep.
But kind of the replacement for that is the ecosystem that I was just talking about of these kind of shared nothing modules that communicate with interface types. We hope to kind of build, you know, a whole ecosystem that is doing this stuff. And so if you want file access, you know, you'd be able to import something that would give that to you, potentially, you know, limiting what you can access only to a certain directory, right? So you can access this Scratch directory, but you can't access my .ssh in my home directory.
Mm-hmm.
When we talk about that communication, does interface types, does it define an ownership model of some sort? Or like, are we copying memory as we go between these? Or if not, how do you deal with like borders between garbage collected languages and not garbage collected languages and things like that?
Yeah. So there is a copy implied between each side. And yeah, that's basically there to make sure that you're not sharing the memory, because that's kind of the vector into, you know, corruption, heap corruption, and, you know, getting rid of the sandbox properties that we care so much about. But what's nice is, you know, with the eventual full interface types that kind of allow programmatic lifting into an interface type and then lowering into a concrete type on the other side, that will be like only one copy, and it will be kind of like directly into and from the representations that each module would kind of like natively want. It's basically, you know, as good as you can get, implying that you do have to have one copy, right?
Got it. So thinking then about the implications for application architecture as we talk about these things, we're going to want to have modules that essentially are self-contained relative to data, where, you know, a module is going to own a set of data and you want to keep the communication between them relatively minimal in terms of data size, ideally.
Yeah, ideally. I think it depends on the component, right? Like copying a string is pretty fast, you know, like memcopy is quite fast, but like it also depends like how nested is the loop in which you're calling it, right? And so, I don't know, there are architectural things that you can do. You can kind of like make one module own the data and then kind of hand out like identifiers saying like, this is essentially a pointer to this data. And whenever you want to ask something about that data, give that back to me. And, you could almost imagine it as like an object, and that's like the little self. And then you call each method to get little bits of data, but you don't ever get the whole thing. This is kind of actually what I did with the source map library, which is like, we have to parse the whole source map, which it's a debug info format. I guess we didn't talk about that. It's a debug info format that maps, essentially like minified JavaScript to unminified JavaScript back and forth, or say, JavaScript to the original coffee script or closure script or whatever that it compiled down to. And so we have to kind of parse that and get the full mappings. So we know this line corresponds to that line and this file corresponds to that file. But like whenever the debugger, for example, stops in a location, it doesn't need the full mappings, right? It doesn't need everything. It just needs to know right now I'm paused at this location. What's the like real source location for where I'm currently paused at? And that's a tiny amount of data compared to the huge map, right? And so you just kind of expose an API that allows you to keep the full data set kind of in the original component and then just make little queries where you get the little bits of data out on the other side.
Yeah, that's really interesting. How much overhead is there in terms of calling between modules? Is this like roughly equivalent to a function call even within a module, or is it higher cost?
It's a little bit higher cost than function calls within a module, but not too much. Basically, maybe we're getting a little bit too bogged down into details, but like there's a register for the VM context that kind of keeps track of like what is my current Wasm instance and what are the bounds of its memories and things like that. And that stays in a register. And when you call across instances, to a new module, you have to kind of like swap out that register with the new instances register. But like, so if you're doing a micro benchmark, you'll see it show up. But if you're doing any sort of like actual work anywhere else, it's going to be lost in the noise.
Yeah, well, and that means that it's extremely viable to treat these things as essentially objects in a lot of ways.
Yeah.
You could say, this module owns this data, and you can call methods that are essentially accessors on it when you need the data.
Yep, exactly.
And really minimize the amount of copying you do. That's super cool. So as we move towards this world, what do you think the implications are for how we develop applications? And are there particular domains of applications that are likely to benefit or sort of be driven to adopting this sooner?
Yeah. So with any kind of like new ecosystem, the more different it is, the harder it is to port existing applications to it, right? And so this is pretty different, right? Like JavaScript environments today don't have capability-based security and kind of allow, ambient access to the network or to disk or what have you. Unix generally allows the same. There are ways to lock it down, but like by default, it kind of allows ambient authority. Most popular platforms aren't like this. And so porting existing applications, depending on how large the application is and how many things it's using and stuff, like it could be hard, right? Similar to like, porting a desktop application to the web can be pretty hard, right? Especially the larger it is. But that tells me that we'll see more like new applications being developed, kind of, greenfield applications. And then where are we, deploying this stuff first? Well, us Fastly are doing it kind of in serverless environments where in general, you already have kind of like smaller, micro applications. So I think that's relatively easy to kind of bring over to this new paradigm. And another kind of domain where we've seen a lot of excitement for WebAssembly, and I think will work well for this kind of ecosystem, is games that want to have like plugins or mods where, say, hey, you want to, change X, Y, or Z about the game. Here, give us a WebAssembly module, and that's kind of like what you'll write it in. And then it's sandboxed from the rest of the code, and you can't kind of break out. You can only use the game APIs that we give you. Or, basically any kind of like plugin architecture, maybe for a digital audio workstation, something like, I don't know, what are popular digital audio workstations? I guess like Ableton and Reaper and these sort of things, they're taking these, audio signals or, MIDI or whatever, And then that goes into one plugin that, provides a filter. And then there's another one that's a compressor, or another one that adds, a chorus effect. And each of these could be their own little WebAssembly module communicating with interface types to kind of apply their transformation on that signal along the way. And then you know that it's not going to break out of the sandbox again, and it's not going to mess with your desktop or whatever. It's just going to work on the audio like it said it would. So that's kind of another area which this would be a really good fit.
Awesome. Nick Nisi, did you have any more things you wanted to dig into?
I think you covered the other question that I had. Maybe you already answered this, but this makes sense to me from having a serverless Wasm environment like this. Does it also make sense to run JavaScript in a browser through Wasm?
Yeah. If I were to imagine use cases where that made sense, it would be very contorted. I think really, you have really top quality JavaScript implementations in the browser. And, you don't need to do these kind of tricks in order to bring JavaScript to your environment because you already have it.
Right.
And, if you have CPU bound JavaScript, it will get JIT compiled, and, you'll have state of the art implementations making your code fast as far as throughput goes. Yeah. If you're on the web, use your web browser's JavaScript implementation.
Cool. And then another question is, can you think of any triggers or things that developers should be on the lookout for using this as a potential solution to a problem that they have? Is there something that would identify this as a problem?
Yeah.
Or as a solution?
I would say whenever you're looking to have your users be able to run custom code,
mm-hmm.
and you don't trust them, and you kind of want to have, but you still want to have them be able to kind of plug into your architecture and customize things. That's basically what this is designed for.
Nice. Okay.
So we develop Wasm engine, which we kind of focus a lot of work on making it easy to embed into other applications. But there's a bunch of different choices out there if you find one that works better than Wasm time. Yeah.
Nice.
Yeah, I feel like the web's security model was by necessity pushed to a place where things had to be sandboxed, they had to be secure, because suddenly you've got all this untrusted code that's going to be running.
Mm-hmm.
And now WebAssembly is basically allowing us to say, hey, that's a good idea for any type of code we might want to run. Let's pull that in.
Yeah. And we can, rather than have one sandbox for, the whole tab or something, right? We can have, sandboxes for each different component, which is really nice. In general, trust things less. If you don't have to trust it, then don't, right? Even if you do trust it, don't trust it.
I feel like that's a good show title.
Yeah.
Trust things less.
I'm not paranoid,
Awesome.
I swear.
I feel like if you're running code that you didn't write, paranoia is a very healthy attitude.
Yep.
Awesome. Well, I think we've covered a lot of ground. I think I'm still sitting here kind of in shock, absorbing all of
Me
it.
too.
Yeah. Nick, do you have any other things you want to leave us with or let us know about before we wrap up?
Well, I really liked your intro music, and I was wondering if one of you produced that, or who did the music.
Yes. All of the JS Party and Changelog, generally all of the Changelog family of podcasts, their music is produced by Breakmaster Cylinder. And
cool.
So they have some great stuff.
Yeah, I'll have to look them up.
You'll get another taste because we're going to close with an outro shortly.
Perfect.
But awesome. Well, if there's nothing else, then thank you so much for joining us today, Nick. I think this is a really interesting topic, and I'm super excited to see where it continues to go.
Yeah, thanks so much for having me. This was a blast.
Thank you.
All right. And if you're listening to this not live, you're listening to this on your podcast, and you want to join in, you want to be a part of the party live when we do it, we do record live and publish to YouTube at the same time we do it every week, Thursdays, 10 o'clock Pacific, 12 Central, 1 Eastern. Check out changelog.com/live. You can join with us in Slack in real time, and you are what makes this a party. So For all you listeners, we'll catch you next time. This is KBall signing out.
We are gearing up for our next Front-End Feud episode, and we need your help. Fill out the survey at jsparty.fm/ff, and you could win a free JS Party t-shirt. Once again, that's jsparty.fm/ff, like Front-End Feud. JS Party is produced by Jared Santo with music by The Beat Freak, Breakmaster Cylinder. Next up on the pod, Chris, Amel, and myself discuss all the things that go on before you write a lick of code. And we also analyze Dan Abramov's post, Is NPM Audit Broken by Design? Stay tuned for that episode. We'll have it ready for you next week.